Hello everyone. Experiment number 3 is about filters and how we can implement filter in a DSP board. The one that we have is from Texas Instruments in the lab. Filters have a lot of applications. Maybe one of the most important one is to remove the noise from a signal. So assume that you have a sinusoidal signal which is affected by noise, and you want to input this to a filter circuit. So this is a filter signal, and this filter, if it is designed properly, is gonna give you your sinusoidal signal at the output. We have a variety of filters. The most important one is low pass filter, high pass filter, band pass filter, and band reject filter. So the low pass filter, this is going to be the frequency response. So if this is the gain or the amplitude, the gain, and if this is your frequency, so then this is going to be the response. It means that you have fairly constant gain at the low frequencies, and when the frequency goes higher and higher, the gain is going to drop. That's why it's called low pass, because it's passing the low frequencies. For the high pass frequencies is the opposite way. So if this is frequency gain and if this is the gain, you are going to have this frequency response. It means that for high frequency you have fairly high gain or constant almost, and as the frequency is decreases, the gain is going to decrease. That's why it's called high pass frequency. It means it's passing the higher frequencies. If you mix a low pass and a high pass filter together, then it's going to give you a band pass filter. For a band pass filter, this is going to be the frequency response. If this is F, and again this is going to be the gain. By the way, gain is defined by output voltage divided by input voltage. As you can see, for the middle frequencies you have a fairly good gain, but when the frequency increases, the gain goes down, and again when the frequency decreases from the, let's say, the first band pass limit, again the gain is decreasing. So this is called band pass, and the last one, band reject, has exactly the opposite. It means that you are going to have a fairly low gain in the middle frequencies, and as the frequency increases, the gain increases, or as frequency decreases, again gain is increasing. This is called band reject filter. So how do we implement it in the DSP board? In order to do that, we have to use FDA tool. So what we do, we are going to have our ADC module on the model, which is connected to a filter, and filter is connected to DAC. The ADC is getting the signal from function generator, and then the filter is going to filter the signal which is coming from ADC, and the output of DAC is going to be connected to the oscilloscope. So what happens, we are going to change the frequency here. So let's say if the filter is a low pass filter, meaning that this is going to be the frequency response. This is again gain, and this is your frequency. So what I do, I'm going to have a sinusoidal signal here. So what I expect to see, if the filter is a low pass filter here designed by FDA tool, so what we are going to do, we are going to use FDA tools to design the filter. So if a low pass filter is designed, so when I increase the frequency on the function generator, and of course there's the knob on the function generator that you can increase the frequency. So if the frequency increases, I should see a lower and lower amplitude. So let's say for, I would say 100 Hertz, I'm going to see a signal like this. If I change it to 1 kilohertz, I'm going to see a more attenuated signal. And let's say if I change it to 100 kilohertz, I should be able to see only a very attenuated and weak signal. So this is a low pass filter. And for the high pass filter, so if I design a high pass filter, it means that again the circuit that I have, this is my filter, and let's say this filter to DAC, to scope, and this is to function generator. So if a high pass filter is designed here, it means that this is going to be the frequency response. That means that if I have my sinusoidal signal coming from here and I start increasing the frequency again, so for high frequencies I should see a fairly good sinusoidal signal. Let's say this is for 100 kilohertz, and for 10 kilohertz I should be able to see a lower one, and for 100 hertz either I don't see anything on oscilloscope or I'm seeing a very attenuated signal. So this is the way that I can check if this filter is designed properly and if my low pass filter is designed properly. So in this experiment you have to change the parameters of filter to design low pass, high pass, and you design variety of filters. You design Chebyshev, or you can design elliptics or Butterworth. So 3 type of filters you can design using FDA tools. I'm going to run FDA tool in MATLAB to show you how to input the parameters. So you type FDA tool, and the wizard for the filter design is going to pop up. So on the left side you can see that the low pass, high pass, and band pass, and as well as band stop filter options are here. This experiment is going to ask you to do band pass, high pass, and low pass. I'm going to show you how, for example, we do low pass and how we input the parameters. So for low pass, the low pass is going to be checked here, the low pass filter, and we need to design IIR filters. It's asking you to do Butterworth, Chebyshev, and elliptic. So I'm going to do Butterworth here, and for the order, just stick to the minimum order. You don't have to change anything. The tricky part is this part, which is the frequency specification. First of all, don't forget to change the sampling frequency to 8000 hertz, and then the experiment is giving you the parameters for omega p, which is omega pass, omega stop, and the gains for pass band and stop band. which are noted by alpha P and alpha S. So these four parameters, omega P, omega S, alpha P, alpha S, are given in the lab manual. The tricky part is that you should know that, for example, the omega P for the passband is 0.3 radian. This is a discrete frequency, and FDA tool wizard is not accepting discrete frequency, uh, so you have to change it to the hertz. In order to do that, the formula would be the discrete frequency, which was zero point 0.3 times sampling frequency, which is 8,000 hertz in our case, divided by 2 pi. If you do the calculation, 382 hertz is the passband frequency, and the same calculation for stop band frequency. So zero point 0.7 times sampling frequency divided by 2 pi, that's going to give you 891 hertz. So I'm going to enter these parameters here. So I enter the parameter here. 382 is for 8 band pass, so 382. 891 is for stop, and then if you go here, alpha P is 0.5 dB, so I'm going to change this to 0.5 dB, and alpha S is 50 dB. These are all given in the lab manual, and then I'm going to say design filter. When you design filter, you can see that the filter is passing all the frequency up to 382. So this is almost 382 hertz because this is 0.5 kilohertz, which is 500. So this is almost 382. And at 890, which is here, we have minus 50 dB, which is coming from here, the 50 dB attenuation is coming at 890, and this is a low pass filter. Why? Because it's passing the frequency, the low frequency, and as the frequency is increasing, the attenuation is getting higher and higher. It means that less signal is going to pass through the filter. So this is a low pass filter. Next part, after you do that, you have to export to Simulink model. I already have a Simulink model, which is my ADC module here. This is the ADC module. The DAC block here. So the DAC block are here. Make sure you double click on ADC and make sure the sampling rate is like 8 kilohertz. There are a variety of options, 32, 44, 48, and 96, but make sure 8 kilohertz is the one. Make sure your ADC source is line in, not the microphone in, and the samples per frame 64 is also there. So these are the parameters. For DAC, make sure the sampling rate is also 8 kilohertz. For a 6713 board model to work, the DAC sampling frequency should be similar to ADC sampling frequency, so this definitely has to be 8 kilohertz, same as ADC. The word length 16 bits and normalize and wrap are going to kept the same. So here, if I say go to File menu and say Export to Simulink Model, and then I say Realize, I click on the Realize Model, you can see that the filter is created. So this is the filter block, which is actually an equivalent of this design. So this is a low pass filter. If I connect the output of A to D converter to the filter, the signal is going to be read by A to D converter. Is going to be fed to the filter. Filter is going to filter all the high frequencies and pass the low frequencies, and the output, which is a low frequency signal, goes to the DAC, and we know that this DAC is connected to the line out as we explained on the very first experiment. So basically, if we apply a sinusoidal input to the line in or to the ADC board, then we are expecting to get a low frequency signal at the line out. You can see the wiring diagram in the picture. The function generator is providing the signal to the line in. So signal is read by the Texas Instrument Board CT DSK6713, and then it goes through the A to D, and then the filter is going to filter the high frequency signal, and the output is going to the DAC. DAC is connected to this line, which is line out. Line out is going to the channel 2 of the oscilloscope. At the same time, in order to be able to see the input that we fed to the board, the input is tapped and is connected to the channel 1 of the oscilloscope. So channel 1 is monitoring the input, channel 2 is monitoring the output, and when you change the frequency, you have this keys to go to different frequency, from low frequency to high frequency. So when you change the knob and you switch to 10K, 100K, 1 megahertz, you shouldn't be able to see much of a signal when you go to the high frequency. When you switch to the low frequency, anything below 300 hertz, then you should be able to see that output and input are pretty much the same, maybe just a little bit of attenuation, because the filter always has an attenuation, and the filter that we designed is not an active filter, so you get some attenuation, but it is not a considerable attenuation. While, as we said, for high frequencies you get a lot of like attenuation. Then this was for the tutorial for the low pass filter. For the high pass, you can always switch to the different like different thing. You can go back to the model and change it so that instead of having a low pass, you can have a high pass or band pass. And don't forget again to do the calculation to change the discrete frequency to the hertz. And again, don't forget that the sampling frequency for both ADC and DAC block are set to 8 kilohertz. This is all about experiment number 3, and I hope you learned enough so that you can do the experiment in the lab without any problem. Good luck.